Okay, so guys, today we have the pleasure to have Johnnie Gray in today's QUINFOG seminar. He's from Caltech and he will tell us about the combined picture quantum dynamics on arbitrary graphs with tensor networks and multiple belief propagation tools. So thank you very much, Johnnie, and whenever you want, you can start.
Yeah, thanks very much. It's a little bit early here, so sorry if I seem a bit slow, but it's a real pleasure to give a talk to you. So thanks for the invite. Um, the title is a bit of a mouthful just to get in all of the different elements, but essentially this is a kind of tensor network simulation method that uses some stuff from belief propagation that we've been working on recently. It's mainly this top paper here, which is partly a tensor network simulation by me, and also this sparse Pauli dynamics simulation by Tomislav. But some of the kind of more theoretical kind of developments started in this paper here with Nicola. So yeah, just to give an overview of the talk very roughly, essentially two parts. The algorithm is a quantum dynamics algorithm, so it's a very generic thing. We have some time expectation of some, I guess, discrete evolution, maybe gate-based, and we just want to compute its expectation value as a function of time. And one of the main new things in this is that we're using a PEPS and also a PEPO, projected entangled pair state, as well as a projected entangled pair operator. And we're evolving one in the Schrodinger picture and one in the Heisenberg picture, and then combining both of these to kind of accurately capture the dynamics. And the thing that enables being able to do this is two of these belief propagation tools, this lazy 2-norm BP compression and this lazy 1-norm BP contraction. And I'll explain what all of these things mean. And then the main application that we'll show is this recent IBM experiment where they did a simulation on their quantum chip of this 127 quite large lattice kicked Ising model that is some kind of like heavy hex lattice. It's essentially a hexagon lattice. And there's now been many papers simulating this. I've just noted two particular ones here, which are kind of related. One is kind of a pure PEPS, and one is a kind of pure PEPO simulation. I should say I'm kind of assuming some familiarity with tensor network stuff here, but do please jump in with any like questions or clarifications you have as we go. So yeah, the experiment, just to motivate this all, it's a kind of kicked Ising experiment or dubbed. So it's not like not really like a pure real-time evolution, because we have gates which are quite far from the identity. But they implemented the following kind of quantum circuit. So each layer in one of these time steps, you have this like ZZ rotation entangling gate acting on all pairs in this lattice here. And then you have some like X rotation acting on every qubit individually. And this kind of rotation in one direction and then kind of pairwise entangling in the other generates, complex entangled dynamics, which is not, exactly solvable in the general case. It is solvable at certain angles of this theta h here. At one end, there's no entanglement, and at the other end, it's a Clifford thing. So there's certain reference points, but in general, the point of this experiment was that this didn't have a kind of exact solution, and their claim was that some standard tensor network methods really failed quite drastically, whereas their quantum chip didn't. And it's an interesting regime that this experiment was taken in now, because it's kind of semi-physical motivated. It's kind of this bang evolution, which has some connection to physical systems. So it's not a random quantum circuit where you're just trying to produce random bit strings. but they have too many qubits to do just a kind of brute force state vector simulation. The circuit is too deep to do some of the more advanced kind of exact tensor network contractions that I've worked on. The geometry of this lattice is also too far from being a tree or 1D like thing for MPS simulation, which they showed. And in the general case, there's also far too many T-gates for some kind of Clifford simulation. So all of the methods that have kind of quite well understood errors or exacts are not immediately applicable. And the question becomes, how do we approximately contract this? So this is just a schematic of the entire tensor network representation of some observable, say like the Z observable on some qubit of this circuit after 20 layers. And it's some very large tensor network that we need to basically try and approximate. And one thing we have worked on, which I thought I'd just flag, is you could just try and do like a fully automated approximate contraction. So there's a few people who have tried this now, and we have a recent effort where you can really just take, an arbitrary tensor network and you do some optimization to try and find the way to approximately contract it. But for the moment, this, like, just the sheer number of tensors in this huge thing makes the optimization a bit hard. And there's also this very special direction in like a quantum dynamics tensor network, which is that you have some kind of unitary time-like direction. And at the moment, it's hard to kind of put in information about that to these completely automated contraction schemes. And you do have to treat it a little bit differently because, of course, the unitary time just taken on its own is not compressible. It's like a full rank operator. So for this, we thought we'd develop some kind of manual scheme, which nonetheless works on arbitrary like geometry in terms of the quantum circuit, but really exploits the time-like dimension. So this is the overview of this simulation method. I've just called it combined picture simulation because we're mixing this Schrodinger and Heisenberg. But the idea is essentially this: we form our big tensor network describing the evolution. So in the beginning, we'd have some pepper representing the operator we want to measure, and importantly, this could be like a high weight Pauli. It could have support on many different qubits. We have our initial state written as a PEPS, which for many cases would just be the zero state. And then we have some kind of pepper representation of the evolution. And you can get this simply by, splitting your gates spatially or, from some trotterization and then just grouping the tensors into layers. So the combined picture simulation is to take the PEPS and evolve it to some intermediate time, tau, forwards, take the PEPO and evolve it backwards in time to some tau plus 1, so these are adjacent. And then we have some very, very large overlap between a high bond PEPS, this PEPO, and the conjugate of the PEPS. And the motivation to do this would be that, unlike using an MPS or something, we get to exploit the geometry of the circuit by embedding it in the PEPO and the PEPS. If the circuit has kind of limited entanglement growth in the state, we get to exploit that. And if the operator itself has limited entanglement growth, for example, if you are close to or in the Clifford regime, then you get to exploit that in the PEPO evolving. So at a high level, this is what the simulation looks like. But the main questions are, as you're evolving this PEPS and evolving this PEPO, how do you actually efficiently compress it back down so that these bond dimensions don't become very large? And then finally, when you have this overlap at the end between a very high bond dimension PEPS and PEPO, how do you perform this contraction? And this kind of mixed picture thing in 1D with MPS and MPOs has been looked at before, so it's not a completely new thing. So our answer for both of those questions is to use some belief propagation tools. So as we evolve this Pepsin pepper, how do we compress it? We use this thing we've dubbed lazy two-norm compression. So the lazy bit stands for the fact that we never have to form an intermediate higher bond PEPs or PEPO, which is very computationally advantaged. The two-norm bit refers to the fact that the algorithm effectively runs on the two-norm of the object. So for the PEPs, you have to form the norm of the PEPs by just, tracing over all of the physical indices, and the BP runs on that. Or for the PEPO, it's a kind of like double sandwich where you trace over both of the up and down indices simultaneously. And if you run BP on this object, then what BP gives you is a kind of gauge to simultaneously compress everywhere in your state or operator. And I'll go into the details of that later, but that's the effective overview. And then the second tool is that how do we contract this huge overlap? We also use a lazy BP, but this is a one norm BP. So rather than forming some two norm object, it just runs directly on that overlap. It's also lazy, which basically means the same thing as here. And in this case, the object, we're not trying to compress it or find some reduced representation. What BP gives us really is like an estimate directly of the total contraction, including normalization. So it's really a different way to approximately contract a very large network. Okay, so what is belief propagation? It's like an iterative message passing algorithm where each of the like local message passing updates you can understand basically as a tensor network contraction. So given some tensor network like we have here, just with a single tensor per these blue dots connected by the bonds, we define a pair of messages for each bond. So at this tensor here, we'd have one message coming from this tensor and one message coming from this. And these messages are really just vectors of the same size as the bond. So, you could take this tensor out and you could contract it with all of its neighboring messages to get the scalar. And
Johnny, so to understand it, so right now the blue dots will be connected by identity matrix, essentially, that connect all possible values of the, and you're replacing that with a lower rank projector or something like that?
Yes, here, yeah, you can imagine though, there's an implicit identity on all of these. The BP algorithm iterates. You would start with these as maybe like the uniform distribution, just ones, but it could just be a random starting point as well. And at each round of the iteration, for every tensor, you take one output index and then you contract all of the messages apart from that into it. And that gives you the updated message for that round. And just by performing all of these contractions over and over again, what usually happens is that the messages converge on some fixed point. And the messages essentially represent some belief about the distribution of values that this index could take. So I'm just giving a very brief kind of procedural introduction. The point is that each of these contractions is just a very local, very cheap contraction because it only involves contracting vectors into a tensor. And we run this, for many iterations. So information kind of propagates around the system. It's not like a purely local thing. And once it's converged in, traditional BP, you would estimate some classical marginals for sampling or some other thermodynamic quantities. And BP has a very long history in statistical physics and computer science that I can give you references for if you want, but I won't.
Sorry, just to understand. So can we say that this is kind of an improved simple update scheme? So if you were to kind of truncate PEPs times the PEPO, would you define as an improved simple update scheme or?
Yes. So BP, it turns out, is essentially like running the square of simple update. And there's a paper which shows it formally converges to the same point. That's when you run it on a like wave function.
I see.
The advantages are that all of the things you're doing are just contractions, rather than doing some linear algebra, SVD and QRs and things, which makes it a little bit more efficient and versatile. But yeah, you can think of it as like simple update.
Okay.
Kind of.
Thanks.
Here I've just drawn it for a like classical tensor network. So this might be representing like a classical partition function. And so it's like, it basically represents a scalar and you just have one tensor per site. But of course, we're interested in like quantum things, and a quantum tensor network, you would have essentially like, you know, a physical degree of freedom at each site. And then if you wanted to compute quantities, you would have to form the two norms. So you'd have to trace out all of these in the standard way. So it's running BP on a quantum thing is like a fundamentally slightly different operation to the usual BP. But what BP does give you is, because of this, you know, very cheap individual procedure, you can take, like in the classical case, you can run it on a tensor network with like millions of tensors. So it really gives you like access to a completely different scale of tensor network in some cases. And particularly for like kind of random long range connections and things, this is a regime that like almost all other tensor network methods would fail in. And of course, also because these contractions are very simple, you can have very big bond dimensions. So yeah, usual BP is run on some classical positive probability distribution, like one tensor per factor. In the quantum case, we form this two norm thing, this either sandwich of the PEPs with its conjugate or PEPO. And when you do this, what happens is you basically explicitly at each site form like a positive object, not positive in terms of the entries, but positive in terms of, you know, a linear operator. And this is itself is not new. There's quite a bit of literature about running BP on quantum states, and there's this connection with simple update that was recently elucidated as well. What is a bit more new is running BP on something which doesn't have this positive structure. So as soon as you put in an expectation between your quantum states, there's no longer like a positive local structure. What you have is just like a Hermitian structure. And so there's no real analog to where BP is usually applied in classical setting, because of course this thing, which would represent a partition function, can be negative in the quantum case. Okay, so just to talk about the first kind of element of this BP we developed, which is lazy belief propagation. I said because the message updates are simply contraction, you can very easily imagine that rather than a single tensor at a site, what you really have is some uncontracted collection of tensors. And you can still perform all of the updates quite easily, because you just take your messages and say you zoom in on this one here, for example, and we have a whole collection of tensors within a single site. The messages now will have, you know, multiple bonds, one that connects to each of the bonds between this region and this region. And so everything here is still exactly the same as in the usual case. We still have all of these just different messages, but they're now tensors with multiple bonds. And each of the updates, rather than just being a contraction of vectors into a tensor, is some kind of tensor network contraction that we have to use, you know, some highly developed exact contraction techniques for. And we have, you know, very good exact contraction methods now.
And Johnny, sorry, does it make sense to also assume some structure for these messages? So here the message you express it as a full three-leg state, right? Could be an MPS or could be something else. Have you tried that?
Yeah, we actually, this is not published yet, but we have done this with an MPS as this message in the time-like direction. And that seems to work very, very well. And I think it's connected to, some works with you guys.
Yeah,
this
okay.
Kind of transverse contraction stuff. Yeah.
Okay, thanks.
And also there's this paper here called Block BP, where they also have this kind of setup, also with the MPS message, but in that case, it's like you have a kind of spatial placetter for PEPs, and the message gets contracted through like that. And then also this tensor network message passing paper. These are both very recent things. They both work with this kind of decomposed tensor network per site of a belief propagation protocol.
Thanks, yes.
So just to get a bit more specific about how we use this to do the compression, imagine we have our PEPs and we now compose it with the next layer of gates. So we have a kind of two-layer object. And what we want to do is find the next PEPs representation at some lower bond dimension chi. Similarly, and this is kind of exactly the same procedure, just with a few more indices. You can imagine we have our PEPO at time step t, and we want to compose it with the next two layers of gates, one on either side because it's an operator. And we want to find the reduced bond dimension PEPO representation of this next site. So we're both going from a collection of tensors per site back down to a single tensor per site. So the first step of this algorithm is that you need to form this two-norm thing. So this example here I'm showing for the PEPO case. You can imagine this would be like a PEPO tensor, and this would be one of the gates from the unitary evolution PEPOs. And to form the two-norm, we have to obviously take this thing with its conjugate, trace over these physical indices, which I've just noted in the green. And then so what you'd end up with is this network per site. And obviously your messages now would be like a six-dimensional tensor connecting all of these things. And you would now just run it on this this new tensor network of the two-norm with these six-dimensional tensors being exchanged. And once it converges, what you can do is you can interpret these messages as essentially being an approximate representation of the canonical gauge around a bond. And for some details on this, there's also this recent nice paper by Tyndall and Fishman. And from these messages, you can basically directly compute these projectors, these oblique projectors, which will optimally compress the bond down to your target bond dimension. So you run the algorithm, you get all of these messages, you compute all of these projectors, and then you can insert all of the projectors around a particular site. So you'd have the six tensors in here, and then these projectors around them. And of course, now you can contract this directly without ever forming the intermediate large thing here, because you have these projectors already. And so you can go directly from this kind of complex representation back down to a PEPs or PEPO with reduced bond dimension by inserting these projectors lazily. And it's kind of similar. It should be mathematically identical to what's called super orthogonalization, which is a kind of simple update style compression. But the real major advantage is because it's all lazy and we insert the projectors lazily, you can compress like something that would have an enormous bond dimension if you actually formed the intermediate right back down by using this lazy BP. And this is like a very cheap and like generic primitive that says, give me any tensor network which has multiple tensors per site, and I want to find a representation of it with a single tensor per site of a given bond dimension, then this is just like a kind of plug and play primitive that you can use. So I think it should be very useful in general. Okay, so next is the contraction part. So imagine that we've evolved our PEPs using this compression method all the way to some time tau, and our PEPO using the same method to some time tau plus 1. We then have some sandwich, some 3-layer sandwich. Sorry, yeah.
Just a question. So these messages are always probability distribution, so they're always positive, right? Even though
no. So in this case, yes, because of the way we set it up, this object is positive, and so you can see there's like 3 indices here to 3 indices here. So they're positive in the sense that you can interpret them as a matrix mapping from these indices to these indices.
Yes.
But they might have some negative entries. In this case, I'm about to explain, they're not understandable as positive objects in the same way. And this is a kind of new thing that we don't have a good handle on theoretically, but it nonetheless seems to work.
Okay, thanks.
So yes, we have this, imagine it as a 3-level sandwich of our PEPs, PEPO, and PEPs. And, hopefully we've been able to achieve very large bond dimensions. So like locally, our tensor network will look like this thing down here with our PEPs, PEPO, PEPs. And if this bond dimension is large, then even though you can get to this point, exact contraction is definitely out of the question. And even approximate boundary contraction is just really not possible either because of the size of these bonds and the type of lattice we're working on. So this is where we also invite a different type of BP tool, which is this lazy 1-norm BP. So here, again, we're running BP on this kind of lazy structure here. So now these messages are a kind of 3-tensor, 3-leg thing, and they don't have this positive structure, as I was saying. But nonetheless, you seem to be able to run BP and to have it converge on this network. And then, so, running it would look like this, passing the messages around. What you do once you've converged is that there's this expression for the free entropy of the equivalent classical model. And this is the kind of the Bible on these belief propagation methods, if you want to look this up. And you can take that expression for the free entropy, which is really the log of the partition function. And if you take the exponential of it, you can interpret this as like a contraction of local quantities of our converged messages and the network. So essentially the total global contraction of this thing is given by taking each of our local lazy tensor groups and contracting in all of the converged messages and taking the product of all of these things, and then dividing by the overlap in all of these connecting messages. And this is kind of like accounting for some, overcounting of these messages being contracted here. And this is super nice because unlike usual kind of cluster methods for computing quantities, it's an estimate of the global contraction. So it's no problem to do like high weight, delocalized observables, that kind of thing. It's also implicitly normalized because all of these messages appear both on the numerator and denominator. And so we can directly estimate the norm of the PEPs or the PEPO. And what's more, it's also, we know in the limit that it's exact on trees. So there's still, some limit that we understand of why this should work and why it still seems to work quite well for loops. Are there any questions on this part? Okay, so just to recap.
Sorry, I was a bit late to unmute. Sorry.
Okay.
Can you explain again where the normalization factor comes in? Because it's not immediate to me to see the
Yeah. So, well, so it's not clear why this should. I mean, the derivation of why this gives you the an approximation of the partition function is something that is not, you can't just easily see.
Okay.
But the only thing I'd note, for example, is if you have this pair of messages here, what you can see is that if you have some arbitrary scaling factor on this one, then that will obviously change the value of this numerator. But because it appears also in this denominator here, and essentially because you counted it too many times, you divide by it in this kind of thing, and that gives you the
okay, thanks.
Okay, so just to recap, having introduced all of these things, we construct our circuit or evolution observable tensor network that involves, spatially splitting gates and grouping them into layers. This is all very easy and cheap. We evolve the PEPs, the red thing, forward in some time using this lazy two-norm compression. We evolve the PEPO backwards in time using the same compression. And then finally, we use this L1BP contraction to estimate the global contraction of the overlap. And obviously, you can change this time. If you make it completely, if you make tau the full time, then you just have PEP's evolution. And if you make this tau 0, then you have just PEPO evolution. And those are kind of two limits we study in the paper. But generally, we studied what we'd call the mix method, which is just half and half evolution. And that lets you capture a huge amount of entanglement in the state and operator at least. So just take a sip of coffee. So applied to the IBM experiments. So if you apply these methods to the circuits I introduced at the beginning from this IBM paper, then with a fairly moderate chi of 64 and a GPU and not very much time, so all of these results in less than 3 minutes, you can essentially visually converge all the quantities, including these high weight observables and the depth 20 circuit for the quantities they studied. And in the original paper, all of these things had, if you just use a standard MPS, or they also had some ISO-PEPs methods, they were all, visibly quite catastrophically bad in certain regimes. And what's more, we can go up to really quite a large bond dimension of 500 with this method. And at that point, these quantities are essentially all converged without using any extrapolation to something like 0.1%. So certainly not numerical precision, machine precision, but for the comparative to the experimental bars, and in many cases what you'd like to see form just general simulation, these could be considered converge. And we have many details in the paper about how we assess that. So the exact results are shown as well. For the top three, I think because we have some slightly more advanced exact contraction methods, we were also able to compute this quantity here, which wasn't in the original paper, which is some weight 17 observable, and that all matches. And then the main quantity of study is this depth 20 magnetization on site 62, which there are no results for, exact results for, but we're fairly confident that the curve basically looks something like this. And so it agrees largely with the experimental results, apart from one point, which we suspect is probably just some kind of artifact from their noise mitigation.
So this D and E, so the D is a product of X Pauli matrix and 8 Y pilot matrices and 1 set matrix, something like that?
Yeah, exactly.
Okay. And the last one, set 62, is set on the 62 spins? Or
No, this is actually just Z acting on the qubit 62. So it's a single site observable.
Okay.
Yeah. So for all of these accessible regimes, we can match the exact quantities where we have them. In this regime, we don't have exact numbers. So, and it's a heuristic method. So how do we assess convergence and accuracy, particularly for this kind of L1 BP contraction that is quite a novel thing? And that's a lot of what we do in the paper. First, just to assess the compression error. So during the compression stage, we're just using the BP to gauge the tensor network before we truncate. So if we weren't truncating, there would be no error introduced at all. And so this is a much more, I guess, familiar source of error, because as you increase chi, you know that everything becomes exact. What we do have is, because we can compute these non-local quantities, we can actually directly compute the norm of the PEPs and the norm of the PEPO. And these things, because it's unitary evolution, we know they should be 1. And so we can essentially track the deviation from 1 as some kind of proxy for fidelity of how much of the state or operator we've chucked away. And so here we have what we're changing on the x-axis is this angle theta h. So we're going from an easier regime to some hard regime where we're having to truncate a lot, almost all of the states, and then back up to some easy regime. This SPD is like the sparse polydynamics. It's some operator picture. The PEPO is obviously operator picture as well. That's why these both, work exactly in the Clifford limit over here. And then the PEPs is like doing pure PEPs evolution with our method. And then this mix is where we're combining the Schrodinger and Heisenberg pictures. So the main thing to take away from this is that as we get into this hard regime, you can see that by mixing the Heisenberg and Schrodinger picture, you can effectively retain a much larger proportion of the norm of both simultaneously. And that's why you can converge, or you don't have to truncate the state so much if you're only evolving each half of the way, essentially. And that's how we get a kind of very high norm in this regime here. There is still some kind of hard scrambling regime where all of these methods fail. Essentially, the entanglement in all of them becomes too large. But this coincides with a point where all of the variables go to 0, at least all of the local ones. And so it's an interesting question whether there are interesting models and circuits where you have this kind of really fast scrambling thing, but it doesn't just produce, essentially like white noise and, 0 local observables everywhere. Maybe I won't talk too much about this, but essentially because we have access to the norm, we can plot our convergence not just with respect to chi, but with respect to the norm. And what you find is that these PEPs and mix methods have really quite a monotonic behavior, where as you ramp up the chi, your norm goes up and you quite reliably converge, from one side to the expectation operator. The more challenging thing to assess is what error we're making in this final L1B contraction step. So obviously, where exact quantities are available, we see that it agrees to kind of 0.1% precision or something. But beyond that, we had to employ a few different methods to check this. So one of those is that for like a pure PEPs evolution, what we can do is use some kind of sampling procedure to generate bit strings. And then use exact contraction of the amplitude network to perform unbiased importance sampling. So, it's not too important to understand this, other than it's a way to completely independently estimate the certain quantities, as long as the bond dimension is not too high. And so this we find is also consistent. And also, for just doing a pure Pepper evolution, we can check these things just by doing exact contraction up to some more limited chi. So at least in this model, we're relatively happy to claim that these are converged and accurate results given all of our albeit heuristic methods, which I can run. And I'd recommend reading the paper if you want a good understanding of how we do these checks as well. So then the question becomes, like, what aren't we capturing? Or like, what, when should this fail? And one kind of very elucidating example is if you just take a loop model. So we're doing exactly the same IBM kicked Ising model, but now just on a single 12 qubit loop. This is kind of like a very hard thing for BP algorithms in general, because what happens is that you have some excitation or something here, and rather than going out and dispersing out through the lattice, what happens is the message essentially gets passed round, and then it hits the site again and just gets passed round and round. And in fact, it's basically like a kind of, you can't tell what size of the loop is. It's like a kind of infinite model. So this in some ways is very challenging for usual simple update and BP style algorithms. And what I'm showing here is the exact results, which is the green line. PEP's cluster, which is like the usual simple update way of computing observables, where you run BP or simple update on just the state, and then you make reduced density matrices from it and compute the quantity. And then this L1 BP thing, where you insert the operator first and then you run BP, and so you break the translational symmetry. And then our mixed method, which is essentially the same. And
sorry,
what's
Johnnie,
interesting is that,
what is the x-axis here in this picture?
So here, this is actual steps. So this is like real time.
Okay, thank you.
And so, yeah, the interesting things here are, if you take the standard PEP or simple update method of computing observables, then it kind of catastrophically fails. It's like it can't see the size of this loop. And so what happens is you just get this blue line down here. Whereas this kind of L1 BP method, where you inject the operator and then run BP, so you're kind of passing around information about where the operator was. What happens is you actually follow the general behavior of the observable pretty well, but you miss some kind of interference fringes. Then at some later point, you also start to lose accuracy just from the bond dimension growing large. And this is kind of interesting because it suggests that there's some kind of intermediate regime between when we would kind of think of simple update clusters working well and more traditional full environment tensor networks. It's just there's some regime in between them when these L1 BP contractions can probably give quite reasonable results. You might also ask what happens on a dense lattice. So traditionally people think of BP as not working on lattices with short loops or strong correlations around short loops. So this is exactly the same simulation steps on the x-axis and this kicked Ising model. Now I'm just running it on a 20-site square lattice and looking at the Z00 observable. And here we find the results are very satisfactory. There are some slight inaccuracies here, and eventually you run out of bond dimension and you get this kind of drop here, and some slight improvement over the PEP's clustered method. But at least in this case, you can see that there are certain cases where even a dense lattice with short loops is not going to be a problem for these methods.
A question here, Johnny.
Yeah.
So in this case, for example, I imagine that the messages are not translational invariant, right? So how do you choose the path to update the message and get them converged? So do you have to go through all of them? Is there some specific? So I guess you start from a random choice of all the messages, and then you start updating them. What's the kind of heuristic for that?
So that's in the simplest case, you'd start with the uniform distribution. So just like filled with ones for every single message. And then you do a parallel update. So you'd update every message using the messages from the previous step. And then you reinsert them, and then you do it again. And there's lots of tricks to try and improve convergence, where you do like a sequential update, where you update one message and then immediately reinsert it. And these are all kind of areas of current study in BP.
Okay.
But in general, you can just imagine you start with ones everywhere. And then you just iterate by updating every single message. And then you just run this for, I don't know, however many iterations it takes, usually between 10 and 100 or something to converge.
I see. Okay, thanks.
What I will mention here is that if you're familiar with PEP's methods in general, you'll be aware that like usually getting to like a chi, or sometimes called D, of like 8 or 10 or 16 is like very, very high. But using these methods, like it's really, I just generated this on a single core, I think, with a chi equals 64 PEPs. And going up to like chi equals 100 for a 2D square PEPs is really quite tractable, which is some kind of fundamentally, new regime just in terms of scale, I think, for these 2D things.
Johnny, is it correct to say that your wave function will anyway be a product state or not? Because you contracted with this weight, right? They are separated. Is it correct?
No, I don't. I don't think it's as simple to understand as that.
Okay.
Because you put in the operator and then you let belief about its value like percolate around the whole network via the message passing. It suggests that for a single site, there is a good enough model where the environment is separable, but that you could still have a very high bond dimension connecting you to the environment. But what BP really is saying is that there's some tree approximation to the environment of a particular site that gives you good accuracy.
I see. Yeah. Okay. Yes. Thanks.
Okay, so this is one case on a dense lattice where it works, but then here, just by changing the observable, we find a case where you would say it does not give satisfactory results. So here we're just moving to somewhere inside the lattice, and now, we don't get terrible results. We get the general behavior with this mixed method or the PEPS method, but we really don't capture this quantity here. And what's more, it actually really struggles to converge. So in some sense, when BP struggles to converge, it kind of heralds that the accuracy is not going to be very good if it does, because what you have are these competing fixed points with different values, and it can't work out which one it wants to collapse into. So it's definitely not going to be a kind of in the current state, it won't be just immediately accurate on all things.
And Johnny, can't you sample these different? So can't you say, okay, let's take more than one fixed point of the BP and use them, having a kind of an average of them in a certain way, or?
Yeah, so it's actually quite hard to it's quite hard to converge to different fixed points intentionally. Usually there's only one that will converge to without some help. This paper I have with Nicola, this replica symmetry breaking, that's in fact exactly what that method does. It says, there's these exponentially many fixed points, in fact. And there's this thing called survey propagation, which is an extension of BP, where you are implicitly summing over all of the exponentially many different fixed points. And that's kind of quite advanced theory stuff that I don't particularly understand. But yeah, so that's exactly what many methods try and do, at least in the traditional BP. None of them have been applied to quantum setting yet, though.
Okay, thanks.
Johnnie, here you have shown that, well, it matters that your system is open boundary and not all sides are equivalent. Can you apply these methods to periodic boundary conditions easily, or it becomes more?
Yeah. I mean, what certainly, at least in terms of like the computation, it's applying it to open boundaries is essentially the same cost as periodics is essentially the same cost as open. You would possibly expect it to be harder to converge because you have this like translational, this extra symmetry and these extra loops. So I'm wary of saying that you can, it's going to work as well on periodic boundary systems.
It's like the problem of the ring you showed before, no? That if it's close, like in the ring before, you have the same problems that messages are passed around.
Yes, yeah.
Okay.
The single loop is a very particular example because the correlations have nowhere to go. You can imagine that, like, actually, if you take a large periodic system, that's actually going to be more favorable for BP because these messages are basically going to, there's many more paths for them to disperse around and produce some kind of average behavior. Whereas actually these small lattices and especially small loops are particularly difficult because everything comes back so quickly. But yeah, it's something we haven't looked at in detail, but it should be very possible to study periodic sim things quite easily.
Thank you.
And so this is a kind of failure that I've mentioned here, but the point would be that there's all of these more advanced BP methods. There's this generalized BP, and so they would give you some slightly different knob to turn rather than just bond dimension. What you'd have to look at probably, and we haven't done this yet, is extending BP to like clusters or plaquettes or the first order loops and those kind of things. And all of these tools exist already. So probably the way to extend this to this kind of lattice would be these kind of generalized belief propagation things. So there's quite a lot of hope that they could become quite a general tool, even in the case where you don't just have a sparse graph. Okay, so I think with that I'll finish. Just to conclude a bit, this mixed Pepper picture is nice because you get to exploit state entanglement, you get to exploit operator entanglement, and you get to exploit the geometry of the problem. And using these BP things, we can really extend all of these tensor network algorithms up to the point where you're really bound by memory. You're just saying, what is literally the size of tensor network I can fit on my GPU, which is a kind of slightly different limit than we're usually used to with full update or something. And the tools we do to use this is this L2B2 compression, which is like a very generic and efficient method to just take an arbitrary tensor network and compress it back down. And it's, because everything is just an automatic local contraction, it's very easy to apply this to real or imaginary time evolution or, some noisy Krauss operator evolution. Is really like a very generic primitive. And then the more kind of unusual thing is this L1 BP contraction, which we showed enables, performing some contractions, which would be way, way beyond what you could do exactly or using the standard approximate boundary methods. And it gives you something slightly beyond what simple update and cluster approximation can do. In particular, you can access non-local quantities like these high-weight observables, although it's not going to be, perfect for everything. And in particular, it kind of enables working with large D pepos. And I think because these have traditionally been so expensive, these have not been developed very much, but it possibly allows us to think again about doing like DMRG and stuff in higher dimensions, where you really have like a representation of the energy as a pepo and that kind of thing. And I'll just plug these libraries that I developed in the group to do these sensor network simulations. And you can also, in fact, I recently uploaded the code to perform all of these things, so you can also check that as well. And with that, I'll say thanks very much. Thanks for listening.
Thank you.
Okay, so thank you very much, Johnny, for such a wonderful talk. So now we have time for a couple of questions. So any volunteer?
Well, I had one technical question. So you mentioned before that you create these long structures per site. In the case of the pepos, it's up to 6 tensors per site vertically. Yeah. In that case, you are using complex messages as tensors, or you're using vectors. I didn't get it very well.
Oh yeah, in fact they are complex numbers. Yeah. So you would initialize the message connecting, for example, these 6 things just as all ones, and then as soon as you contract it, with another one here through this network, because these are unitary operators with some complex numbers, the messages you get out will be complex as well.
But it's complex not only in the sense of complex number, but also complex necessarily it's a tensor, and you represent it as a matrix per state, or you represent it as 6-leg tensor?
For here, we literally represent it as a dense tensor, so just a single tensor. Obviously, that's not scalable to like an arbitrary number of legs, but it's, you can a single tensor can be easily many millions of elements, so it gives you a lot of freedom to really put in a lot of bonds between sites.
But you reach 500 one dimension with that? No, it's smaller, no?
Yeah, no, we reach 500 with that.
It's pretty large.
So in that case, these bonds here would be 500, and then each of these would be 2. So the messages would be like size 2 to the 24, which is very
a few million. Okay.
Yes.
I have a question, Johnny. Did you, besides this small loop, did you benchmark it on 1D out of equilibrium things?
Well, no, because in 1D, like open boundary conditions, it really is, it just goes back to like a kind of canonical TBD style algorithm. The gauges you find are just the same as like the the Vidal gauge, and so
yes, because you would find a kind of fixed point from left and right, and
exactly, yeah, and there's no loop, so everything is exact, and the gauges are like optimal gauge.
Okay. Yes.
Okay, since there are no more questions and we are already on time, so let's leave it here. So thank you very much, Johnny, for this talk. And well, despite of the time difference, we managed to make it. So yeah, we are really grateful to you.
Thanks for the invite.
And well, hope to see you sometime, somewhere in some congress or something. So take care, and for the rest of you, see you in the next QUINFOG seminar. Bye bye.
Thank you.
Bye. Thank you very much.
Thank you, John.